All right, I think I'm live. Probably been live for a minute or two, haven't I? Right, hello everybody. This live tonight is basically going to be half an hour of GCSE. So if you're an A-level student watching, if you're panicking about A-level paper 1 tomorrow, then come back at 8 o'clock, or indeed skip forward half an hour if you're watching the rerun of this. But basically from 8 o'clock, I think it says down this side here, I'll be doing A-level stuff, some last minute paper 1 preparation for all of you. But yeah, hello Dr. Musical, hello Joe, hello. So I'm just going to get rid of some people. Basically, I'll just ban people if you do bad stuff in the chat. Okay, so yeah, I hope all of you are doing well. I know for those of you doing GCSE, you've already done paper 1, and paper 2 seems like a long way away, but there's lots to learn in that time. Tonight, the first part of the stream, we're going to be going through some paper 2 stuff, really kind of AQA paper 2, but it's basically stuff that anybody doing their paper 2s for GCSE is going to find useful. And then, of course, after that, we're going to be going on to A-levels. Joe, you've done your AS exams. Sticking around for the streams because they're great. Thank you so much. I'm sure this will help reinforce stuff. Some of the stuff I'm doing later in the stream will reinforce the stuff that you cover in Year 12. But I really hope, Joe, that for you and everybody else who did AS physics exams over the last few weeks, they've gone okay. And hopefully that's given you a bit of confidence, and actually it's a good way to kind of be in a real exam at A-level, see the standard, but of course knowing that as you go into Year 13, actually the course gets a lot more interesting. Okay, and of course people like Dr. Musical doing GCSEs. Yeah, GCSEs are good. I mean, GCSE physics is a great course, but A-level physics is so much more interesting. There's a lot more maths, which is like when it really gets interesting. I feel that you can really use the maths to explain things properly. I will be starting Maxwell Williams A-level at 8 o'clock, so come back in about 25 minutes. Okay, yeah. Okay, by the way, you don't need to be in a panic. I'm just going to hopefully just reassure you that all of you at the moment do know lots and lots of good stuff. So the question today, this one is a GCSE question. This is from one of my practice papers. Of course, if you're an A-level student, you can have this on in the background, and this should basically be a nice little bit of gentle revision to kind of get you back into this. What is meant by the extension of a spring? So the extension of a spring is basically how much longer, or indeed actually sometimes how much shorter that spring gets. And it's going to be equal to the final length minus the original length. Okay, so extension, sometimes we use the symbol E, sometimes X, sometimes delta L, but this is basically the change in length of that spring. Now the elastic limit is basically the point, and if we actually look on, sometimes we have maybe a force extension graph, we basically get a point where if we go beyond a certain limit, we don't get this directly proportional relationship between the force and the extension, and we go beyond the elastic limit, and that means it starts to exhibit plastic behaviour. So that's behaviour that means that the material won't go back to its original dimensions when the force is taken away. So the elastic limit, basically, if the force exceeds a certain size, then the object won't go back to its original dimensions. Okay, that's all it is. Right, just going to read some of the comments. A lot of people there, I know there's lots of A-level people, a lot of people saying they're cooked. This has kind of been a popular phrase I've seen in the comments, so it must be like the word of 2024 is, for the students doing A-level physics, the word is cooked. So yeah, but you know, it's all going to be fine. Right, okay, then we have a question. Actually, this is a nice A-level question as well. The spring rests horizontally on a flat, frictionless surface as shown in figure 6, which is up here. It's pulled to the right by a constant resultant force of 1 Newton. No other horizontal forces acting on the spring, and we know there's going to be no friction, because if it's a smooth or frictionless surface, that means the friction the size of that force is equal to 0. Explain what will happen to the spring, include details of the motion and any temporary or permanent changes of shape. So basically, what we can see is that the resultant force is to the right. So it will accelerate to the right. And this is basically a special case of Newton's second law. So we know there's a resultant force, and that's going to cause this mass to accelerate. So this is just Newton's second law. Okay, but, and this is the thing that I think a lot of people might not get, is the fact that if we've only got a force to the right, then the spring isn't going to extend, it's going to stay in the same shape. And by the way, this is GCSE at the moment. It says down here, it's GCSE until 8 o'clock. But of course, even A-level people might kind of miss some of these bits out. We can say that the spring will not extend. So the spring will not extend as there is no force acting to the left. And basically, if you have a spring which is being deformed or extended or compressed, you need to have two forces acting on that. So they might be pulling it, they might be pushing it, or they might be twisting it. Okay, and there's no force acting to the left as the table is frictionless. There we go, that's all that question is. Okay. We then have a scenario where the same spring is used to make a Newton meter, sometimes called a spring balance, which is a device used for measuring forces. So if you have a Newton meter, then we can actually calibrate this to measure the weight of an object directly, not just its mass, but its weight. And as the spring extends, a triangular pointer attached to the bottom indicates the force written on the plastic housing of the Newton meter. So this is kind of your very, very simple kind of like Key Stage 3, Year 7 kind of practical that you could do. So, as the spring extends, the extension is directly observable, but the scale printed on the Newton meter tells the user the applied force in newtons. Okay, so all of you actually playing along at home, 4.3, the first part. What's the word, so this is stating the word that best describes the following. So what do we call the process of marking a scale on the Newton meter that reads force rather than extension? So, bit of a kind of a word quiz, like a spelling bee kind of thing. What word would we use to talk about marking a scale on the Newton meter that reads force rather than extension? Because what we have here is the force, or the weight in newtons. It's not a distance in millimeters. Okay, and of course, if you're at A-level, then you should know about this as well, Scarface. Okay, so what word do you reckon we could use for the process of marking a scale on the Newton meter that reads force rather than extension? Okay, people are being rather slow in the chat tonight, and I know there's a lot of A-level people watching. Okay, I don't know, random error. No, it's not an error. Okay, it's a bit like hangman, so... Okay, so people don't know the word. We're going to do a bit of hangman. So what letter would you like first of all? The first letter that I get is the one we're going to put in. We'll see how the hangman gets on. So Dr. Lizard, I'm afraid it's not parallax error. N. Okay, we've got an N. A, says Scarface. Okay, we've now got a Z. Okay, somebody said Z, that's the ground. E. Okay, there's not an E either. Okay, Joe, finally, yes, we have the answer. So the word is calibration. So what we're doing here is we are calibrating an instrument, which means rather than, although it might measure the length in millimeters or centimeters, we're actually calibrating it to convert our length, maybe in millimeters, into a force in newtons. So this one over here, the word is calibration. Right, the next one. What is the smallest interval between the force readings marked on the scale? So what we have here is the smallest reading is going to be equal to 1 newton. So we can basically say it's plus or minus 1 newton. What's the word for that? Callum D, straight in there. excellent work. The word is, as Callum has said, resolution. Okay, right, the last one. Okay, a mistaken mark in the scale such that a force of 0.5 newtons is indicated when no force is applied to the Newton meter. So, this one over here. Right, we've got sine Zoku. Easy! Yes, excellent stuff, sine Zoku. And also Anissa. We've got the word zero. To be honest, it's actually two words, but this is zero error. I mean, it's not broken, Charlie. It's kind of just what we call a zero error. So basically, if there's a reading when no force is applied and it kind of gives a numerical value, that's what we call a zero error. Okay, so some good stuff there. Right, is there a calculation next? No, there's not. There's a question about forces and something to do with paperclips. So again, this is a relatively straightforward question. And I'm sure a lot of you will have done something similar. So this one here, figure 8, shows a chain of paper clips held up by a permanent bar magnet. So we've basically got this maybe held in a retort stand, and then you just stick paper clips onto the bottom, and then you stick another one on and another one on. Each paper clip acts as an induced magnet, and the paper clips are labelled 1 to 4. By the way, I drew all of my pictures in this. So anytime you look through one of my practice papers, all of these images, I mean the Cybertruck we saw yesterday, the graphs I drew myself, I think there's some nice images. That one there, that took a while. But I've got various pictures that I drew myself, and basically I've been formatting this, and although I had other teachers helping write some of the questions, actually the pictures themselves, the diagrams, are all done in my own distinctive style. So it took so long. This particular diagram took ages. Okay, right. So for this one, describe the difference between a permanent magnet and an induced magnet. Okay, so we could say that a permanent magnet is always magnetized. But an induced magnet is only magnetic when placed in a magnetic field. Okay, so that's like our GCSE answer. So I would say that this is the main thing. Is the permanent magnet can always be is always going to be magnetic, so it doesn't matter if it's not in a magnetic field, it's just going to stay as a permanent magnet. So this one over here will always have a north and a south end. These are induced magnets because they will only become magnetized in the presence of a magnetic field. And actually I would say that I feel a lot of the magnetic questions you get in physics, they're actually harder at GCSE looking at this kind of stuff, whereas at A-level they kind of ignore kind of bar magnets and you go straight into like magnetic fields and then how charged particles move in those fields. Okay, now I will be doing, by the way, for a lot of people there, I will be doing AQA help later on. I just can't show AQA papers. It's just copyright. I don't want to have my channel taken down for the sake of that. Somebody's asking about Pythonian, which by the way is an amazing name. I absolutely love that. What's the transition between GCSE and A-level physics? To be honest, I reckon there's quite a big jump. And I think the biggest jump sometimes is for lots of people who are watching at the moment who find GCSE quite easy. And often you can go, well, I don't need to do much homework. I'll just look at CGP revision guide or watch a couple of, my videos maybe with the Lego in it. A lot of people find GCSE quite easy and suddenly they really have to work at A-level. I would say that this book here is what you need. If you're a GCSE student, and this is a shameless plug, but you buying the book allows me to keep making live streams, which helps support you as you go through A-level physics. So I would say that if you get this book, there are questions for every day from about a month's time. So you can do questions in July and August over your summer holidays. And then as you go into September and October, there's even more questions. But this will get you completely ready for A-level physics. I guarantee it. If you do these questions, then you will find the transition super, super easily. So this one here is book 1 of my daily workout. Go and buy it if you are a GCSE student. Okay, Describe what is meant when two forces acting on an object are balanced. So this question, although it's in the context of magnets, it's just about forces. So if two forces are balanced, we can say that the forces are equal in magnitude, but opposite in direction. There we go, that's all it is. Right, state which object is responsible for the downward force on paperclip 4. So this one here, 5.3, let's see what you think it is. So there's a downward force acting on this paperclip. Which object is responsible for the downward force on paperclip 4? So again, of course, A-level people, I know there's some of you watching now. What is the object that causes the downward force on object 4? Okay, heads, correct answer straight off. Excellent work. Really impressive with that. Weight is not the correct answer. Weight is the force, but the question says state which object is going to cause that weight. And this is GCSE, by the way, but actually hard GCSE stuff. So weight, gravity, not the correct answer. We're not asking what is the force, but which object is responsible for that. So looking in the thing over there, Ezra and Heads both say the Earth. Basically, although you've got the paperclip up here, you've got the Earth which is pulling it down with a gravitational force, and the paperclip is going to be pulling up on the Earth with the same size force, but the weight acting on this is caused by the Earth, because the Earth is an object. Oh yeah. Okay, which object is directly responsible for the upward force on paperclip 4? So again, if we think about this paperclip here, there's going to be a weight force acting down due to the Earth, but there's also going to be an upwards force due to something else. So what is, it's not the moon, okay, so which object is directly responsible for the upward force? I would say, and here's the diagram here, which of these objects is directly responsible for that force? I would say it's a magnetic force. We've got 2ACE 8200, I reckon has got the best answer so far. I would say the answer is paperclip 3. Because although the magnet causes this to become magnetized, it's actually paperclip 3 which is providing the force on paperclip 4. So although there's a magnet there which magnetizes all of these, paperclip 3 has become an induced magnet, and it's that magnetic field at the end of this which is attracting force. So I would say for this, it's paperclip 3. Always read the question. And I would say, even if you're doing A-level physics tomorrow, then you can still highlight keywords if that helps you to kind of really understand the question. Most of the time, people make mistakes in their A-level exams and GCSE exams, not because you don't know the physics, and I guess if you were to sit down and discuss that question with somebody else, you get to the right answer. It's about reading the question and really actually understanding what it's asking at the time. Okay, the north and south poles of the permanent magnet are indicated. Write letters N and S on each paperclip in figure 8 to indicate the location of the northern magnetic poles along the paperclip chain. So if that's south and that's north, then it means that this paperclip here, this end must be south, and that must be north, and then that's south, and that's north, that's south, and that's north, and that's south, and that's north. Okay, so there we go. That's all there is to it. Yeah. Okay, if the intermediate paperclips 1 to 3 were removed, paperclip 4 would fall to the ground, even if the permanent magnet remains in place. So imagine what we did now was we basically got rid of all of these, and we only had basically a scenario where we had the permanent magnet at the top, and we had paperclip 4 down here. So, explain why this is. Basically, what we can say, and I think the distance definitely matters, as Nabil says. Dr. Musical, yeah, magnetic fields are too weak, and this is due to the distance. I would say heads, it's still actually in the magnetic field. It's just down here, the field is too weak. So what we could say is first of all, we need to think about the field, and of course we could maybe think about the field lines. They're going to go from sort of north to south, and they are still going to sort of go out into space like this, and there will, still be some kind of weak magnetic field. Okay, so that's kind of like a really rough sketch there. What we can say maybe is that the magnetic field around the permanent magnet becomes weaker with distance, and I think this is what a lot of people have already said in the chat. So I will look at the chat in a second. It's just difficult to do both. Okay, and then you could say that this means the force up due to the magnet on paperclip 4 is less than its weight down. So if we were to maybe think about just the forces on this thing here, there would be a force upwards due to the magnetic field, but the force down due to the Earth causing the weight force due to gravity means that the weight is bigger than the magnetic force up, and that means there'd be a resultant force down, so it would accelerate down. So, but it isn't floating in the air. If we were to just take them out, we'd find that it isn't floating. It would float for like a fraction of a second, then it would start to fall. Okay, and that means it would accelerate towards the ground. And there we go. That is the answer. So basically what we're looking at here is, because we don't have these becoming induced magnets, if we just had the permanent magnet and paperclip 4 at this position, if you held it there and let it go, then the magnetic force up is going to be less than the weight down. There'd be a resultant force down, and it would accelerate towards the ground. Okay, and of course it's great to see so many people wondering why they're here tonight, because you've already done your GCSE exams, you've done your AS exams and so on. So I was just going to answer a couple of quick questions. Right, a lot of people, sorry, I'm just going to delete a few people off the channel. Okay, somebody said that you've already finished AS level physics. You're still here because you're still doing physics, and all the stuff that we're doing tonight will still be useful for you maybe in a year's time. Do I know what? Okay, I would say I've got no idea. There's no point trying to guess. You can't predict what's going to happen in the future, especially with AQA and OCR and EdXL. I mean, because what they try and do is they have enough good, solid questions that means everybody gets the marks. But there'll always be those weird 1 or 2 questions that lots of people find a bit more difficult. So I don't know, really. Somebody said that Bison Maths Live was crazy. I didn't actually see it myself, but I know Bison Maths. We've had a few chats, actually. We're going to. I actually sent, I don't know if he's using them yet, but I sent him some webcams. So hopefully he's been using those to kind of help with his live streams. But yeah, definitely me and him will be doing some videos next year. Knowledge or exam technique, I reckon both. There's no point being amazing at exam technique without having the underlying knowledge. Is it true teachers see results a day before results day? Scarface, potentially some people might see it the evening before, but often teachers are maybe emailed the information in the morning, maybe before students. So sometimes your teachers might have seen your result before you pick them up. Okay. Somebody said that paper 1 GCSE went well. Clamor 69. There were some harder questions for EdXL about emission and absorption spectra. Okay, that's difficult for GCSE. Bob Sheldon, good luck. You need it. I see. Is there an equation for phase difference? There isn't actually an equation. It's just like you need to look at the information in the question to try and work out what it is. What shall you do now for tomorrow for A-level physics? Kalsa, basically, if you don't know the physics now, it's pretty much too late. So all you can do is, I'd say, look at some easy questions. We're going to do some in a couple of minutes anyway. And basically try and get an early night, get a good restful sleep. And then in the morning, maybe just look over some of your notes just so you know that you're familiar with the definitions of the things that you need to know. Okay, right. Excitingly, I managed to get some Lego today. So you can see, a lot of you might have recently seen, we've been collecting bits of Lego. Oh, this guy's kind of chainsaw's just fallen off. So this is the Lego series we have so far from Lego Space. And there's a new kind of minifigure here. So shall we open it? Yeah, basically, by the way, this is a work expense. You know, this is my job. I get paid more than I was as a teacher to kind of play with Lego, make some videos about physics. I mean, this is now my life. Okay, so there we go. We've got the minifigure there. Which one do you reckon it is? So, okay, so we've got some bits. Okay, we've got the instructions. Oh, and I think this might well be a new figure. It is a purple one. I know people like the purple one, so this is like what it could possibly be. And we do have most of them. So which one is it? Okay, there's some like alien style head there. Okay, this one has got like some weird like, it's almost like the feet of the foal in The Lion, the Witch and the Wardrobe. So we've got some kind of crazy feet there. We've got like a kind of skeleton torso, which is pretty cool. How do they go together? So they've got like a cape, which I've never really seen a cape like that before. Do you know what? I have no idea. This is probably one of the weirdest Lego figures I've seen. So there we go. It's some like weird alien thing with a load of eyes. And is this like a leaf with some like kind of weird alien plant? I'm sure there's a whole backstory behind who this is. So there we go. We have a new Lego figure. Is it like a predator thing? Yeah, it's like a kind of like an ant style kind of head. So I don't quite know what that is. Okay. Right. This isn't really part of astrophysics. I would say that my favourite of all of these, I've got two favourite characters so far. I think, first of all, I do quite like the realistic space. So this person here in like a spacesuit, I reckon is pretty cool. That's like one of my favourites. So you've got an astronaut there and she's going out on like a spacewalk. I think that's really cool. My other favourite one is definitely this person here. So they've got like a head that looks like a flying saucer. And I think my favourite part really is the torso, because it does look like space. There's like a shooting star there. There's like the Earth and the Moon with some misconceptions there. So yeah, there we go. Right, stop playing with Legos, JT. Okay, right. Okay, let's put this away. If you do want to see more Lego stuff, I do have a couple of videos with some Lego in it. But I do think that a lot of the Lego does explain things quite well. So, A-levels tomorrow. We're going to go on to the A-level part of the stream now. Goodbye, GCSE people. I will see you quite soon. Now, the questions tonight are... these are suitable for everybody, okay? I know these are OCR questions, but it's just a good way to kind of like look at lots of different topics. So these questions are from an OCR paper. It happens to be the 2018 paper. Uh-oh, how's my printing? My printer, okay, the printer's all good. It's a little bit faded at time. So it doesn't matter which exam board you're doing. This is going to be suitable for anybody doing EdXL, AQA, WJC, EdXL International, CIE, everybody, CCEA. Okay, so which of the following units is not an SI-based unit? So this one here is pure knowledge. It's like a super easy question, which I would say takes you about 10 seconds to answer. So if you want to play along at home, is it A, B, C, or D? Which of these is not a base unit? So the base units include things like length in meters, mass in kilograms, time in seconds. Oh my God, there are so many people here. I cannot keep up with this. But people don't know the right answer. So we've got mass, kilogram, second. We also have mole. We have candela. We have Kelvin. And we have the amp. Okay. Okay, so these are the SI base units. So based on that, oh my God, there's so many people watching. I can't even read out all of your names. The answer is a volt. That is not an SI base unit. So the answer is C. So the reason is that a volt is basically the energy transferred per unit charge. Okay, which set of quantities are all scalar? So which of these are scalar? Well, first of all, we need to get rid of the ones which are vectors. So it can't be that. Force, and also here we've got weight. So we've got weight, and force here, acceleration. Those are vectors. B, 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 B. Okay, Light Argent, Scarface, Luke, Hungry Hippopotamus, great name. Meep. There's so many more people here tonight. Where have you been for the last few weeks? I think this is now my 24th live stream for A-level physics this year. So this is like almost coming up to exactly 1 day sat here talking to you guys. The answer is B. Right, the next one. I would say if you get a question like this in the exam, leave it and move on because there's too much text. I apologise, it's a little bit difficult to see. Okay, so we've got a metal block of mass 2.28 has an initial temperature of 82. The temperature of the block after 1.2 minutes is 20. The specific heat capacity of the metal is 130. What's the average power transferred away from the metal block? Now we know that the change in thermal energy is going to be equal to mc delta theta, and the power is going to be equal to the rate of energy transfer, which is going to be equal to delta Q over T, which is equal to mc delta theta over T. Okay, so what's the power? Well, the mass is going to be 0.82. Specific heat capacity is 130. The change in temperature is 82 minus 20, which is 62, divided by 1.2 minutes, so that's 1.2 times 60. So for this, I would not even look at the answers. I would just go straight to the calculation. A lot of people are saying A, and if we do the calculation, we get an answer of 31.3444, which is this one over here. So the answer is A. Great stuff. Why haven't I changed temperature into Kelvin, Scarface? Basically, it's a change in temperature. So we could add 272 to this and add 272 to that, but it's the difference, and the change in temperature is just 82 minus 20, which would be the same as if we did it in Kelvin, because 1 Kelvin is the same as 1 degree Celsius. Greek, the goat. Thank you so much. I really appreciate that. Thank you so much for the donation. Greek the goat, awesome work, great stuff. Okay, a Kelvin, by the way, Tobin talks. Basically, when to convert from one to the other, it's 273 Kelvin is equal to about 0 degrees Celsius. Okay, all right, yeah, 273.15 or 16. Coleslaw, thank you very much for your comments. That was really, really kind. Thank you so much. Right. Okay, so the acceleration of a simple harmonic oscillator is related to its displacement x by the equation A equals minus 25x. So what is the frequency of that oscillator? So for this, we can basically write out underneath it, A is equal to minus omega squared x. Okay. So we know that the acceleration is proportional to minus the displacement, and therefore it must be some harmonic motion. That's like the definition. That means omega squared is equal to 25. So omega is root 25, which is just 5.0. Is that right? Oh, no, sorry. No, sorry. Omega squared, sorry, omega is 5.0, but of course omega is equal to 2 pi f. And the frequency is going to be equal to omega over 2 pi, which is 5.0 over 2 times pi. So we've got 5 divided by 2 times pi, which equals 0.795, which is this one over here. So the answer is A. All of you are doing so much better than me. Yeah. Okay. Right. So how do I get my calculator to do that? I just go to Shift Setup, Input Output, so that's number 1, and then I think it's Line Input, Line Output, which is number 3. Okay, this one here, I would say looks complicated. I'd circle this, come back to it at the end. But actually, the question shouldn't be too bad. So basically, we've got a rod fixed to a pulley. 2 forces are applied. The tension in the rope is T. The system is in equilibrium, so that's important. If it's in equilibrium, that means the clockwise moment is equal to the anti-clockwise moment. Now, the T force here, if that's 20 centimetres and this is circular, then the anti-clockwise, well, first of all, the clockwise moment is going to be equal to 50 times 40. So we've got 50 times 0.40 plus 50 times 0.40. So that's a total clockwise moment. and the anti-clockwise moment is equal to this t times 0.20. Okay, so 50 times 0.4 is 20, times that by 2. So we can say that 40 equals 0.20t. So t is equal to that divided by 0.2, and that's equal to 200. So this one over here, what's the tension? Have I made a mistake there? Oh yeah, sorry. We don't need to know the tension. We don't need to know the moment, don't we? Always read the question, people. RTFQ. I didn't read the question. I calculated the wrong thing. So this is equal to the anti-clockwise moment, and that's just going to be equal to 40 Newton meters. And so here the answer is D. Michael Williams, how's it going? Thank you so much for that donation. Really appreciate it. Honestly, if you have access to your parents' credit cards, then I'm very happy to take donations tonight. And by the way, people, lads, you are not cooked. Sorry. Okay. Yeah. Right. Okay, so yeah, on Mark's scheme it gives us 40 Newton meters. I made a mistake there because I didn't read the question. So the moment of the tension about the centre of the pulley is equal to 40 Newton meters. Okay, so the next one. This is a nice one. I would say calculations, do not look at the numbers, just get straight into the physics. And actually there's often no particular technique. I think that, from my experience, the best way to get good at multiple choice questions is just to be good at physics and have a lot of knowledge and the ability to read questions. So what is the energy required to change 30 moles of the liquid to a gas? Now we've got the molar mass here, so this is going to have to rely on your GCSE chemistry. Now the way I remember it is the number of moles is equal to the mass divided by the molar mass, and that means the mass is equal to the number of moles times the molar mass. So the mass is equal to the number of moles, which is 30, times the molar mass of 0.018. So the mass of that is 30 times 0.018, which is 0.54 of a kilogram. And that means the energy required to change this from a liquid to a gas. So this is our specific latent heat of vaporization. So the latent heat of fusion is solid to liquid. Liquid to a gas is vaporization, and E equals ml. So that's going to be 0.54 times 2,300 times 10 to the 3, because often these latent heats of vaporization are given with kilojoules per kilogram. Okay. Okay. Reese's YouTube channel. It's great to have to see the donation. Appreciate that so much. It's great to have seen your comments all evening as well. I really do like that. So let's see if I can I like these comments. I can like that, can't I? And I think I can like that as well. But yeah, thank you so much for people who are donating. That is awesome. So we multiply that by 2300 times 10 to the 3, and this gives 124,200, which is this one over here. So the answer for this is B. Okay. Okay, I like these ones. These ones are nice. Okay, so one end of a spring is fixed and a force of F is applied. So the elastic potential energy is, okay, so what's the extension of the spring? So if we know that there's a force applied to the end, we know that the elastic potential energy is equal to a half Fx. Okay? What's the extension? We just need to rearrange this to say that 2e over F is equal to x. And therefore the answer is just C. So that one over there actually was 3 marks, as Theodore says, as Anch, Chloe, loads of people are saying Reese's YouTube account, thanks for the donation, and also keep motivated. I like that name, good. Yeah, the answer was C. By the way, a lot of people, if you're doing AQA and you've done 2023 exams as part of your practice, the 2023 exams were too hard. They were just too hard. The teachers know about it. They really kicked off. AQA, I think they knew that they'd given something which is too bad. If you're in an exam, and I said this in my video that I put out the other day, if you feel like you're going to cry because it's too hard, don't worry, because everybody else feels the same. Okay, you're all preparing, doing the same kind of practice papers, the past papers, and that means if you are finding it difficult, everybody else finds it difficult. and they lower the grade boundaries. So don't worry if it gets too hard. But I reckon this year AQA is going to be a lot nicer than in previous years. We'll have to see. I'm going to see some friends and get some papers tomorrow and maybe do a video about it afterwards. Okay, here we go. Another numerical one, so just ignore this. Shout out Mr. Rose. Hello, Mr. Rose. Well done for all your, I suspect, probably good teaching, if people are wanting a shout out. Okay. Back up. Yeah, I reckon it's going to be okay. I've got a good feeling about this year for AQA, and I think OCR, EdXL, they know what they're doing. Okay, so an electron makes a transition between these two energy levels, so it's dropping down. We've got this photon frequency here. What's the value of the energy level X? So for a question like this is like a lovely quantum one. You know, I reckon there's going to be a question which is like this. Okay, we know of course that the change in energy is equal to HF, and that means the change in energy is equal to the Planck constant, which is equal to 6.63 times 10 to the minus 34. We're going to multiply that by the frequency of 4.10 times 10 to the 14 hertz, and that means our change in energy is equal to about 2.71 times 10 to the minus 19. Now, if it goes up to minus 5.4, then the level down here must be a bigger number. Sorry, do I need to ban somebody? Cool, okay, banned, good. Also, shout out to Mr. Mannix. Mr. Mannix, again, I'm sure your lessons are adequate and your children quite like you a little bit. Hopefully that's all right. Okay, what the Sigma? Medwolf, I'll do that for £10, definitely, yeah. Somebody, Heads, says you despise quantum physics. I like quantum physics. I think it's brilliant. I think it's really good. Okay, so that's the change in energy. So it increases by 2.71 up to minus 5.4. And therefore, what we're going to do is we're going to take 5.4, we're going to add 2.71, and this is going to be 8.11. So the answer for this one is going to be D. So it's minus 8.12. So the answer is D. Okay, the next one. This is some statements over here. Get a pencil in case you make a mistake when you're crossing through things. Which of the following are correct for the damping forces on the pendulum? So is the... Okay, so first of all, is the damping force opposite to acceleration? Well, basically... Thank you, Reese's YouTube account. You definitely have access to your parents' credit card, don't you? I appreciate that. Okay, right. That's awesome. Thank you. So, and by the way, am I doing shout-outs now? Okay, Mr. Snow, Mrs. Claxon. I'm just hoping there's no like rude names you're trying to make me say out. But yeah. By the way, shout out to all the physics teachers. I know there might be a few physics. If you're a physics teacher watching, do let me know in the chat, because I know there's some physics people out there. Mr. Shepherd, thank you to Sushi Man 56, appreciate that. Oh, hold on, I've done something wrong with my chat. Appreciate that, I'm just trying to like it at the moment, thank you. Right, okay. Mr. Tomlinson and Mr. Hoyle, shout out to them. Shout out to Mr. Lee. Okay, right. Dr. Scribbins. Okay, right. Mr. Cobb's class, anybody there? Okay, somebody hopes that Max Brown fails. So shout out Max Brown. Max Brown, you won't fail. I'm sure you'll be absolutely fine. Okay, right. Okay, and also Jack Bernard, £5 donation. Appreciate that very much. Okay, right. There are so many people I need to shout out, because all of your physics teachers, by the way, you're lucky if you've got a really, really good physics teacher. There's not enough physics teachers around. So if you've got a nice one who's been motivating and inspiring you all the way through, then I'll just do a shout out to all of your physics teachers at the moment. Right, which of these are true? So if it's accelerating, maybe, so again, draw a diagram. So here's our pendulum. Maybe it's got to this point, it's accelerating this way. Then that's maybe the direction of the acceleration. The force is going to be in the opposite direction if it's a drag force. So is the damping force opposite? That's true. it's always opposite to the direction of velocity. Yeah, so the velocity here would be this way, so the force would be that way. And it's maximum when the displacement is 0. So yeah, at the 0 position, that's when it's going with Vmax. And therefore, because the force, the damping force due to air resistance is proportional to the velocity, you're going to have Fmax as well. So I think 1, 2... Oh, hold on, have I made a mistake there? Oh no, sorry. The first one is incorrect, as people have said. Okay, the reason is that's incorrect is because it will be moving, it will be accelerating down both when it's going this way and when it's going that way. So that means the acceleration is always towards the position of 0 displacement, and that means that the acceleration is always downwards when it's going this way and when it's going that way. So it's going to have a velocity that way and a velocity that way. So that means the direction of the force is going to change. So the first one is incorrect. So it's 2 and 3, and the answer is B. Sorry about that. Okay, right. A few more questions to have a look at. Oh, this is nice. I like this one. So, okay, shout out to Mr. Chohan and Mr. Key and Further Maths. Yeah, Further Maths gang. I'm sure there's a lot of you out there in the chat. Okay, right, the next question then. So we've got a trolley of mass M. So that's got a mass of M, pulled along a horizontal table by a force W, provided by a mass. So there's no frictional forces, the acceleration of free fall is G. What's the correct equation for the acceleration of the trolley? So I would say for this, we know that the resultant force is equal to the mass times the acceleration. Okay, now the resultant force is equal to W. Okay, W is equal to, I'm going to call this M. So that W there is equal to mg. Okay, and basically there's going to be a force W down, but there's also going to be a force tension up in that string. Okay, and basically this resultant force is equal to the weight of that, take away the tension, and that's equal to the total mass, which is the mass of the trolley. Excuse me. The mass of the trolley plus the mass of that weight stack times the acceleration. Now this W over here is equal to mg, and the tension is going to be equal because we know that this mass here accelerates, so we know that that mass, the force in this is equal to the tension, which equals mg. Is that right? Or ma, sorry. This resultant force acting on this trolley here is equal to the tension, which is equal to that mass that accelerates times the acceleration. So mg minus ma is equal to m plus ma. Okay, so that means we want to find a on its own. A is equal to mg minus ma over m plus m. Okay, is that one of those? Oh, do you know what? I've overly complicated it. So that's the weight. So that's equal to weight minus mg minus ma. Oh, do you know what? I've really messed this up, haven't I? Oh yeah. M is equal to W over G. Hold on. Right, Mr. Myers. Good shout out to you from Dev. I think I'm really going to mess this up. So, right, this is the thing. If you get to a point like this, just cancel that question and come back to it later. Okay, I will solve it. Okay, so let me do it again. So, we know that the weight acting down minus the tension is equal to the mass times acceleration, okay, of this particular thing over here. So we've got the weight down minus the tension is equal to this mass times acceleration, and that mass, because we know W is equal to mg, the mass is equal to W over G. So that's equal to W over G. Okay. Now the tension here acting in this cable, if we think about this now, that tension is equal to that mass times the acceleration. So if we put this back into that, we can say that the weight minus ma is equal to w over g. And that means we can then say, is that right? So we can say that w is equal to ma plus w over g. Oh, I've made a mistake, haven't I? Oh yeah, that's that. So that means, do you know what, okay, this one over here, I reckon I'd have just come back to this at the end. So that means A is equal to W over M plus W over G. So this one over here, I would say the answer is D. Okay, I've done that really badly, haven't I? Okay, so basically, pause the video now, have a look at that, and hopefully that makes sense. Right, Mr. Buttle says the answer is D. The answer is D, yeah. So basically, we know that the weight minus the tension is equal to W over GA, and that's the acceleration of this. But that's going to accelerate at the same amount as that. And for that, the tension is equal to the mass of this times the acceleration. Okay, right. Yeah, real physicists know when to skip. I should have skipped that, shouldn't I? Let's just do a nice easy one. So the table below shows some data for two wires, X and Y. They have the same original length. The tension is the same, both at the Bay-Hooke's law. And what we can therefore say is what's the ratio of these two things. Now we know that the Young's modulus is equal to the stress over the strain, which equals F over A over, let's say, E over L. So that's equal to FL over EA. Okay, now they've got the same original length, the tension or the force is the same, but they've got different values of E and different values of A, and we want to look at the value of extension of X over the extension of Y. So we can say that the extension is equal to FL over EA, and that means the extension of X over the extension of Y is equal to the extension of Y times the area of Y over the Young's modulus of X times the area of X. So basically, if we look at this, that's equal to 200 times 2 divided by 120 times 1. So that's the same as 400 over 120, which is going to be about 3.3, and therefore the answer is D. Okay, does that make sense? Sorry, there's so many people looking in the chat. So yeah, hopefully that's all making sense. So what I did here was this thing here. I think here's my prediction. This equation will come up tomorrow for everybody doing A-level physics paper 1s. Extension is, the Young modulus is equal to stress over strain. So the Young modulus is FL over EA. So the extension is FL over Young modulus times the area. Of course, they're going to be the same, and that means the ratio of the extension of X over the extension of Y is equal to the Young modulus of Y times the area of Y divided by the Young modulus of X over the area of A. Does that make sense? Okay. Okay, right. It's crazy. I don't know how many people are on here. How many people are live at the moment? Let's see. I've got about 500 people. Oh my God. This is like a quarter of people doing the exam tomorrow. By the way, it would be amazing to have everybody like the video now, and also everybody in the chat just to immediately put in about the next 2 or 3 seconds, which exam board you're doing. So are you doing AQA, OCRA, OCRB, are you doing WJC, CIE, SIA, IB, whatever it might be? Let me know in the chat which exam board all of you are doing. Okay. Okay, I reckon a lot of AQA people, a lot of OCR people, not as many EdXL people as I thought. But yeah, and of course, by the way, if you haven't already done so, I do need to say this. Thank you so much for watching my videos. If you haven't already subscribed on YouTube, subscribe, because that number makes my ego really increase, which is incredible. There's not many OCRB people. Okay, it's mainly OCRA. Right. An object is dropped from rest at time t equals 0. It falls vertically through the air, and here's the velocity against time graph. So, which statement is correct? It has constant acceleration. That can't be correct because we've got a constantly changing gradient. You says, thank you, we love you. Okay, that's awesome. Okay, do you reckon it's going to be A, B, C, or D? A, B, C, or D, which one it is? It experiences 0 drag at time equals 30. No, because if it's got a velocity, there must be a drag force, and therefore, I like that statement there. Why people stress when the exam's next week, says Munchma Kuchi. Okay, so that's not true either. It has an acceleration of 9.81 at time equals t equals 0. By the way, Dr. Barla, Mr. O'Donovan, a good shout out to you from Alexander. I'm sure you're good teachers, which means obviously they're spending their free time. They're spending their money to get shout out to you. So yeah, it's great to have people like you in their class. Yeah. Okay, it travels the same distance every 10 seconds. Well, that's not true because the area under the graph does keep changing as we go forward every 10 seconds. So that must be the correct answer. So the answer is C. Which Ikra, Silver Crow, Chichi Boom Boom, Ben, Gareth, Royal Kiwi, Riptide Kills, hello again, Jack Bernard. Yeah, great stuff. Right. Okay, this next question here is more about gravitational fields. This one here, although it's an OCR question, I'm not sure if AQA have this in paper 2 maybe. So for this question, we can basically say that the change in gravitational potential is going to be equal to minus GMM divided by 1 over R2 minus 1 over R1. Okay, so that's the equation we're going to use. Now, I don't think there's any shorthand, so maybe this is one you can come back to at the end if you're not quite sure how this might end up. But I would say that if it goes from the Earth's surface to an orbit 1,200 kilometers above, draw a diagram because it's the distance from the center of that mass that we need to do. And so many people forget to add the orbit of the satellite onto the radius of the planet that it's going around. Shout out to Mr. Turnbull Physics. Definitely, Jack, Mr. Turnbull is awesome. Although the other day when I looked for Mr. Turnbull on YouTube, it did come up with Mr. Tumble. So yeah, but his physics stuff is great. So Mr. Turnbull, if you're watching, let's do some collabs. It'd be great to do that stuff at some point. Okay, so that's going to be equal to the 6.67 times 10 to the minus 11, the gravitational constant. We've got a mass of 6.0 times 10 to the 24 times 320, and then we'd multiply that all by 1 over R2, which is going to be equal to 7.6 times 10 to the 6. Shout out to Mac from Ethan. Yeah, Mac, hope you're doing well. Good luck tomorrow. And then we're going to take away from that 1 over 6.4 times 10 to the 6. And when you do all of that, we get an answer of 3.16 times 10 to the 9 joules. So the answer for that is C. So these ones over here, if you know it's going to take you a long time, circle a question, come back to it later. Okay, this one's a nice one actually, isn't it? The volume of 1 mole of an ideal gas is V. The gas exerts pressure P and has thermodynamic temperature T. Which of the following has units of joules per mole per Kelvin to the minus 1? So, here we go. Thank you, young man. Thank you for that donation, all the way from Hong Kong. Thank you so much. Shout out to Albert Einstein. And also, Tiana Dele says, Science Shorts, Physics Online and Z Physics. Yeah, again, it's all great to have other people and, of course, Mr. Turnbull as well. Every YouTuber, I'm building a new studio. It's going to be amazing. So when I build my new studio, all you other physics YouTuber, teacher people, please come along and we'll make some good videos together. Okay, so we know that PV is equal to nRT. So which has the units? Well, basically, pressure times volume has the units of joules. N is a mole. K, where the temperature has a unit of K. And R is joules per mole per Kelvin. So we need to look at something which is equal to R, and if you have PV, which is joules, divided by T, that's just going to be joules per Kelvin. If you've got PV, that's joules. If you've got pressure over temperature, oh no, hold on, PV over T, hold on, have I made a mistake there? Yeah, so basically, when n is equal to 1, then PV is equal to RT, and that means R is equal to PV over T, and therefore this one over here is the right answer. So the answer is D. Okay, so I'm trying to read the comments at the same time. Okay, let's just finish with a nice one. Which graph, number 15 here, which an object oscillates with simple harmonic motion, which graph best shows the variation of the potential energy with distance from the equilibrium position? So often this graph actually comes out a bit like this, okay? And we've got either A, B, C or D. Now if we think about maybe a pendulum, when it's at its maximum displacement, it's going to have the highest potential energy. So when it's at its amplitude or at its maximum displacement, it's going to have its highest value of potential energy. When it's at the midpoint, it's going to be at its lowest point. So the potential energy is going to be 0. So it's going to have to be something like this. So it could be this, this or this. It can't be this one. Okay, this is more about the kinetic energy of that particle. And in actual fact, what we get is a shape that looks a bit like this. So this is a shape that shows the potential energy of a simple harmonic oscillator and how that is related to its displacement. Of course, if you wanted to look at its kinetic energy would be doing this. So that's kinetic energy. Okay, General Cami says, can I shout out Daisy? Her favourite quote is "Skibbity fire in the hole." Yeah, of course I can, General Cami. Of course I'll do that. No problem at all. Okay, and that's basically kinetic energy. And if you had on the same axis the total energy, I'll do this in green. The total energy, provided there's no energy lost to damping, is going to be this green line up here. So remember this when you have a simple harmonic oscillator. Okay, right, I reckon it's like 8:30 at the moment. All of you need to get a nice early night, get a good bedtime. So I reckon tomorrow it's going to be okay. I mean, I've got no way to predict it. I think everybody out there, if you're watching this now, you're in a good place, okay? Hopefully you've seen some of my videos over at alevelphysicsonline.com. If you find that you want to access more videos for year 13, please go and buy a premium plan. If you're feeling panicked, I've got a link at the top of the chat. If you buy a premium plan, then obviously you access more videos. I know it's only a couple of weeks, but also this allows me to keep making videos, and I've got big plans for next year. If you are in year 12, by the way, then you've got another year till this all happens, but go and buy this book. This is the daily workout book this is questions which I guarantee if you do all this work here, you'll definitely get an A star when you do A-level physics exams at the end of year 13. I need to shout out the chocolate cake for Ibtisam. Also, oh my God, there's so many people. Backup says, come on guys, got this in the bag. You do. You're going to be absolutely fine. Yeah. Sorry, there's so many things in the chat, I can't quite read all of it. So somebody says something about my hairline. Yeah, my hairline is going back. But, I did like my A-levels 24 years ago, which is crazy. Mr. Cobb helped at a really troublesome time for somebody. So, yeah, Mr. Cobb, hope you're doing well and people do appreciate the stuff that you've done. Do you need to know required practicals for paper 1 and 2 for AQA A-level physics? Says Peter. Yes, I reckon it's worth knowing about all the practicals you've done, just because there could be an assessment or a question that kind of is based on this. But to be honest, a lot of that you just know anyway. It's using simple lab equipment, but maybe set out in like a different way. Thank you to MK. Appreciate your donation. That's very kind of you. If anybody else wants to continue supporting the channel, then just go and buy a premium plan, or I will be back doing more live streams. Especially after half term, I'll be doing live streams every night from, I think, about the 2nd of June, which is all going to be focused on paper 2. Thank you to Young Man for the $25. OCR gang, yes, OCR gang, a lot of you are out there. Also, Mr. Hasley and Lewis, also, yeah, Physics Online. That's me, shouting out myself. Right, I'm going to leave it there. Basically, go and buy my premium plan. And if you do want to get some more questions ready for paper 3, go to my online shop, which is physicsonline.shop. You can buy practice papers there for paper 3A and for practical skills for OCR and Edexcel. So I'm going to leave it there, I think. I've done enough chatting. Basically, if you don't know it now, it's too late. So all you can do is revise stuff, go over your notes, know your definitions, get a good night's sleep. And in the morning, maybe just have a look at some easy questions just to kind of give yourself that bit of confidence. But I hope all of you do really well tomorrow. And I will see all of you very soon in future lives. And I'll make some more videos. But do let me know how it goes on. Thank you so much, everybody. And good night.